Okay, let's start. So, as you know, we are in the chapter on dynamic programming, which was a completely different perspective on optimal control problems than what we had taken before. So it's not the NLP perspective, but it's a different one. And we started with basically with enumeration and motivated that dynamic programming is a smart way to enumerate. And so the main thing I would like you to remember, which I will repeat, is the dynamic programming recursion. So the main concept is the cost-to-go function, and this cost-to-go function would be defined as a function, let's say, for every time step, k being the time step here. This could be k plus 1, this is k. And for each time step there is a function as a function of state space, and we derived a formula that relates the cost-to-go functions from one time step and the next, in the sense that the cost to go is the optimal cost that you would achieve if you start at that state and you do the optimal actions until the end of the horizon. And these cost to go functions, they obey a recursion, which is given by this formula, where the cost to go function at that time point is given as the minimum over all u actions that minimizes the next stage cost, which could have an index in principle. The stage cost on this transition from k to k plus 1, plus the cost to go that you would end up after this time step if you let the system develop according to its system dynamics, and of course the system dynamics could also be time varying. So this is the main equation I would like you to keep in mind, and that is the essence of dynamic programming, that you basically obtain the optimal cost to go as a function of the previous cost to go. We will discuss this operation in a bit more detail today, and also make some relation with the nonlinear programming perspective and these multipliers that we had before. Before we do that, I want to go to one special case, namely infinite horizon problems. Which is, of course, very often what we are interested in. So very often actually you could think of, you want to do something that lasts infinitely long, and you want to minimize the cost until the end of everything. Sometimes this is done with a discount factor. In the script at the moment we don't have it, but maybe I will just introduce it briefly at the end. So just think of a problem where you say, I want to minimize a cost which now should not depend on the index, so the cost itself should be time independent, and I sum over all indices up to infinity. And my decision variables are all the x and u trajectories, and my constraints are the system dynamics and an initial value, which I can state like this. And also here, please take, okay, now I have a u and an I goes from 0 to infinity, actually, in this case. Yeah? So this could be an infinite horizon problem. In particular, when you want to regulate a dynamic system to steady state, it's very logical. If your penalty is, if your cost is actually a penalty that penalizes deviations from the steady state, then you expect that you are able to actually move into that steady state and that your cost remains 0 there. So this problem is not leading to infinite sums if your cost has a 0 steady state possibility. So now the question is, how could we still apply dynamic programming in this context? And the approach that's also computationally possible is that you say, actually, if there is, if this exists, right? If the infinite horizon problem has finite solutions, which is, of course, not the case for every problem, just just think of a cost which is just 1 at every time point, independent of what you do. This will always sum to infinity, and your optimization problem has not a finite solution. But in other cases, as I said, if you are able to go into a steady state and stay at the steady state at 0 cost, then you would be able to actually have finite solutions. And in this case, it is actually possible to formulate a condition that this recursion needs to satisfy, so that you get actually the optimal cost to go from any state to the very end of all times, infinity. The optimal cost to go, and this optimal cost to go should just satisfy the equation that this j and this j should be the same. Because if you have a cost to go function from one time step and the next one, and you always look into infinity, it's obvious that the cost to go I mean, if you are one time step closer to infinity, you are still as far as before from infinity. So basically the optimal control problems do not change. So the optimal cost to go function, you could actually even define as the minimizing value of this thing, right? So I should actually write, this would be j infinity, I could call it of x0 bar. So for every x0 bar, I could assign this optimal cost. And this optimal cost should then satisfy this equation, because after one time step, it's still looking to infinity. So what we get is, has finite solution j infinity of x, then j infinity, I call it j, maybe I drop the infinity here. So it's just not having any index because it's not time depending. Then it satisfies the following equation. So let me state the equation. The equation is that the j of x is equal to the minimum of L x u plus the same j. This is now the difference to before. Minimized over u. So that's it. It's just a stationary equation now. You could think it's like a fixed point equation for the function j, and this is called the Bellman equation. And that defines the optimal cost to go for an infinite horizon problem. And maybe as a side remark for those that find it interesting, in some cases you might want to have a discounting. So you might, for example, think of minimizing the cost, but costs that occur in the future are actually worth less in the present. So sometimes you add, and in many practical applications you would add a discount factor alpha k here, which is smaller than 1. So alpha is smaller than 1, bigger than 0. And if you discount that, then of course you can make even a finite number converge, right? So this will be finite in many more cases. But the equation will only be modified with a little modification alpha here, just 1 alpha. So this is alpha to the power of k. So interestingly, you can just extend it very easily to the case of discounting. Alpha is a discount factor. That's a possibility if you want. If we set the alpha to 1, then we are at the original case that we just had. And I think I will drop it from now on, just for simplicity. This is just a side remark. So you could even treat discounted problems with this same approach by saying, okay, it's clear, everything that's one time step in the future is just multiplied with 1 alpha and therefore discounted, and that's why I just need this 1 alpha here in this cost equation. So now this Bellman equation can be solved in some cases. Of course, you can try to solve it in a discrete state space. But you can also solve it for the linear quadratic regulator, and we will do that in a in a minute. But before we do that, I want to make a few things and define them. So the question, what is the optimal control here, is also now without an index. And if it's unique, sometimes it's not unique, so correct would be actually this. It's an element out of the set of minimizers of this function. And this whole function we will call j tilde x and u. J tilde of x and u. So this is how you get the optimal solution. And maybe I should say, and I didn't say that in the script yet, that this thing is sometimes called, in other contexts, it's sometimes called the Q factor. In the field of reinforcement learning, they call this quantity the Q factor. So this is the solution, and this is a stationary optimal feedback control. And I would like you to note that in the case that you really want to control a system and you just say, I want to minimize this cost over infinite horizons, then this stationary optimal feedback control is like the perfect thing for you. That's the best thing you want to achieve. And that's like the holy grail that people in optimal control would like to achieve and usually cannot. Yeah, so in some sense, many things, for example, model predictive control, can be seen as an approximation of this optimal feedback control, which is difficult to compute in reality. But it's good to define it conceptually, and also it's good to keep in mind that in some cases you can actually compute it. Okay, so there's like the most important application of this infinite horizon problems in engineering is probably the linear quadratic regulator, and that is very easy to define. It's section 8.4. The linear quadratic regulator, it's called. LQR. And it's just the application of this this infinite horizon theory to a problem which has a quadratic cost and a linear system. So the problem that we want to solve is just defined by an Lx that's just given by something which I define usually with these matrices Q, R, and S. Q, R, S, and S transpose, X and U. Please note that, of course, this needs to be time independent now. So this there can be no index that depends on time. And there is also the system dynamics, f of x and u, which are given by ax plus bu. And you immediately see that if, maybe I should say, with usually this matrix is positive definite. That's the usual assumption. There could be some weakening of that assumption, but with this assumption, most applications work, and then it's also always nicely defined. So the question is, if this is a positive definite matrix, of course at zero the cost is zero, and at every non-zero point it's not zero. You will stay at zero state with zero control. So actually zero is a perfect value where you could stay infinitely long without incurring any cost. So we see that this infinite horizon problem with that cost function actually leads to a finite cost. And now we can apply the stationary equation, the Bellman equation, with these costs, and we will just get an equation which I want to point out to you. Actually, we already derived last time an equation that let me just say, j of x will be given by x transpose p x. And we have already derived last time that if the system is linear, the cost is quadratic, and this cost is also quadratic, then the minimizer is also leading to another quadratic. Yeah? And we derived actually the recursion that the matrices P would satisfy. And of course, if the j here and the j here should be equal, we just need to drop the index on the p in the previous equation, which we can copy. And then we have, where we had the p k plus 1, we just don't have an index anymore. And then we get exactly what we had before, which was something, I need to look it up, but something which had, which started like this and then had these terms. Like this is the inverted term, b transpose p b to the minus 1, and then here was the s in the same term was here, the transpose, and this was s plus b transpose p a. So if we find a matrix P that satisfies this equation, then it is actually solving the linear quadratic regulation problem. And we remember that also the optimal feedback control, this u of x, was then given by a multiplication with a gain, which we could call k. It was just a linear function. And the k was given, and it's the same that we computed last time, so I will not repeat it. This k was given by this, basically this matrix here, this and that. So it was the R plus B transpose P B to the minus 1, and then S plus B transpose PA. So this equation is called the algebraic Riccati equation. In discrete time, because it also exists in a different variant for continuous time. And it's a similar equation, similar, difficult to solve, but just slightly different. And this, this K is the LQR, feedback gain. So this equation, the algebraic Riccati equation, of course you could say, that's a difficult thing to solve. How do I solve it? And there are many different ways to solve it, but conceptually the easiest is probably that you just think what would be the solution for a finite horizon problem. Yeah? It would be the solution where you start with a zero cost at the end and then you accumulate it by using the time stepping variant where we had a pk on that side and a pk plus 1 on that side. We use that for several iterations, and step by step, the longer we go, the longer is, so to say, the time horizon in the background. And if we do that infinitely long, then we will end with a stationary p. So you basically start with an empty p, 0, yeah? And after the first iteration, you hopefully can invert that matrix here, but that is like assured due to positive definiteness. And so it is well defined. So the first iteration P would be 0, the second it would be Q, and then it would be a bit more complicated. And after a while, it will be nearly the solution to that equation. So that would be one way. It's a safe way, but a very slowly converging way. There are other ways which actually use this as a root finding problem. They solve it using a Newton type method, or actually Newton's method. And please keep in mind, or that's like the thing I should point out, this is not a linear equation in the matrix P, right? So there's a P here and a P here. Alone, that would be nice at linear, right? But here we have the P squared and a division by a matrix which involves also P, or an inverse matrix. So this is a nonlinear matrix equation. So to solve, use the dp recursion. Starting at p equals 0, or Newton type methods. And I should point out that because it's a nonlinear equation, like with all nonlinear equations, there could be non-unique solutions, multiple solutions, shadow solutions. So it could be that you also find a non-meaningful solution, but you want to find only the positive definite one. Yeah. How do I say it? Suitably globalized or suitably initialized. To get the P positive definite. So you only want the positive definite solution, which is actually the one, because this is positive definite, the whole cost can only be positive definite, and so the whole matrix P is expected to be positive definite. Okay. So this is, very briefly, one of the most widely used state space controllers in practice, and the fact that you can, I mean, this equation looks complicated, but in MATLAB, you can actually just compute it. So there is an algorithm that people can use easily, and not only in MATLAB, but in many tools. But in MATLAB, for example, it would be something like the command LQR. Sorry. I think it's even discrete, LQR, and then it expects your matrices and system, and it spits out the matrix P and the matrix K. And the beauty of it, and that's also actually the reason why it's so widely used, is that at the end you get this optimal feedback control, and what it is, it's just a matrix multiplication. So the only thing you really need to remember when you want to implement it on a real system is this matrix K. So you don't care how it was computed, I mean via this matrix P and then this complicated expression here, but at the end, if you have 5 states and 1 control, then this matrix K is just consisting of 5 numbers which linearly weight the states in order to give you the control. So it's an extremely simple algorithm to implement. Once you have found the matrix K, it's extremely easy. And then you have feedback that is optimal for this infinite horizon cost and for this linear system. So that's why LQR is so popular. So a very brief explanation of a very widely used tool. So who has ever used LQR in some context before? Or who has heard about it? Okay, the engineers. Okay, so that's good. Yeah. So this was all about deterministic problems until now. And because I think it's exciting, and because I think that it could be useful for some applications where other methods that we teach would fail, I also wanted to present some more theoretical properties or extensions of dynamic programming, which are partly useful, but partly also just interesting to know. But before I present them, maybe there's the need for some questions. Yes, please.
Since this is the Riccati equation,
yes.
I heard the term Riccati iteration. Is that like solving the...
Yeah. I think probably when I say this DP recursion, you could, if you do it for linear quadratic problems, you could call that a Riccati iteration, where you have the index k here and the index k plus 1 here in order to actually iterate. That's what I would think it would mean, but maybe we should look at the literature where you found that.
Yeah.
Mm-hmm. Yeah.
I heard it.
Mm-hmm. Yeah. Yeah. Okay. Mm-hmm. So the Riccati iteration. Mm-hmm. Other questions? Is I think this is pretty self-contained, or is there some stumbling stone, something where you think this is not logical, or this is maybe too fast, or I took too many shortcuts in the presentation? Yeah?
Again, a question.
Yes, please.
For equality and inequality constraints,
yes.
Can the Riccati equation be extended?
No, not really. No. Yeah. Yeah. Yeah, that's actually a very interesting question in a sense. So, as I said at the beginning, if you have inequalities, we would just assign the infinite cost value to the cost L here. Yeah? So wherever they are violated, this cost is infinite. So in principle, this whole theory here you can apply to it. And actually the function j of x will consist of some parts of states which are leading to a feasible solution. And some, actually, imagine you are with a car, yeah? You want to, with this car, you want to drive to a wall and park there, and so you penalize deviations from parking at this, from the parking position. Maybe it's just a one-dimensional car, so you have one state for the position, one for the speed, yeah? And you have some braking limits, yeah? So you can brake as much as this, but not more. Of course, there would be some states, like a speed, if I'm with 100 kilometers per hour, but 1 meter before the wall, that will be an infeasible state. I mean, after a short time, I will have a crash. And so for that state, the cost to go function, this j, will be infinity. And so there will be a region in state space where this cost to go function is actually infinity. So it's actually boring. You don't want to be there. You are anyway doomed when you are there. You cannot do anything. And in the other part of the region, you will still have a cost. And of course, probably it's minimal then at the point where you wanted to park, and positive at other locations. So you can easily incorporate this concept of state constraints and control constraints into the definition of the Bellman equation. But unfortunately, it's it's not possible to represent all this with just one quadratic function of this form jx equals x transpose px, even in the case when your cost was quadratic plus some constraints. Yeah? So if you have a quadratic cost and you have some constraints, like inequalities, for example, even linear inequalities is what would lead us to a QP, you would not have a nice recursion for these cost-to-go functions. So there is, it can be a very complicated feasible set, actually. It's a very complicated region. But yeah, actually, one can show that it's, in that case, piecewise quadratic. So you can somehow do some things, but it's very quickly exploding combinatorially. So you don't want to really, there is no easy equation like that one. But if you would have a quadratic cost with linear constraints, you can prove some properties of this cost-to-go function, which are nice. And actually, part of that will be covered today, but only from a very high-level perspective. Yeah. Other questions? No. Then I would like to, please allow me this little excursion. I want to talk about robust and stochastic dynamic programming, because that's something that will not be covered with other methods. So until now, everything is just an alternative to the other perspectives. Yeah? It's a deterministic optimization problem, which we could also solve with the Newton-type method in principle. Yeah? Because infinite horizon is already slightly different. That's something we could not solve with Newton-type methods because we cannot even formulate it. And even worse, it is for robust and stochastic dynamic programming. And that's what I want to present next. And so, what do I mean by robust optimal control? When you have, this is all very quick, but the idea is quick and the solution is also quick. So what we usually assume is that the system just does what we want, right? So it just, we know the system, and when we choose a control, then it does what we want. In robust and stochastic modeling approaches, we would just say there is some other thing that acts on our system which we do not know. Yeah? So there is another input into our system that could actually drive us into a direction that we did not think is useful. So maybe I put an index k here. So it's this system dynamics that will govern our system. With this, W is unknown to us. And it can be chosen by an adversary So like another player in chess. And then, the two things that I want to present is it's either chosen by an adversary, and that is what leads us to either games, yeah, like chess and so on. But in the context of control, it will lead us to robust control. Why? Because we would assume that the adversary is like nature trying to make our control, the thing that we designed, behave as bad as possible, and then we still want to design it so that it's not really bad. Yeah? So that's what a robust design would be. And the other assumption that it could be stochastic. So we know a distribution. And that would lead to this stochastic dynamic programming. So there could be a probability distribution for this W that we know. Yeah? We know that we don't know it perfectly, but we know its distribution. Or if it's chosen by the adversary, then we would know, hopefully, that this adversary can choose it only from a set. Yeah? So in chess, the adversary should obey the rules, right? And for example, if you think of this car that just wants to park somewhere, you could say there is some disturbances, so there's some wind or whatever acting onto our car, which we don't know. And so these two things could occur in practical applications. And if you think of what would be the optimization problem that you want to solve there, it is quite complicated to even write it down as an optimization problem for the following reason. Because after I decide on an action to do now. After that, the system will do roughly what I predicted, but not exactly because of this perturbation. So one of these W's will become reality. After that time step, I observe the next state. So I know now in which state I am. So I can react to the change, and I will actually even have, so I don't need to plan now like in a normal optimal control problem. Yeah, I plan now all the steps already. I plan them when I'm at the start of a horizon. I can plan all steps. I make a good plan. But in the presence of stochastic influences or adversaries, I will actually adapt my plan after each time step, so I cannot plan one trajectory, open loop, so to say, but I need to plan actually only the next step, and then I want to have as much freedom as possible afterwards. So it's a relatively complicated problem to formulate. In the case that these adversary actions would be from a finite set, I could still formulate it in form of scenario trees, so that is one way. If disturbance A occurred, then I do plan A, and if disturbance B occurred, I do plan B, right? That's what you could do. You could make 2 plans after the first time step, and then you make 4 plans after the second, and 8 plans, and then 16 plans, and so on. So you quickly get a combinatorial explosion. So this would be one way to formulate them as still as optimization problems, but usually you cannot if this is an infinite set. But in dynamic programming, you can still very easily formulate it, at least conceptually, and then also try to use that for approximations. And the way to go is actually very intuitive, I think, if you think of it for a while. So in robust DP, I put an index here, because it could still be a finite horizon problem. So robust DP means that there is basically also the cost, by the way, could depend on the adversary. And the adversary will actually make us as bad as possible, so it will maximize while we minimize. And so if we want to express that the adversary cannot do something, then we will give infinite minus infinity, because the adversary maximizes any forbidden state for the adversary will get the value minus infinity. So in that sense, we can get the same picture as before. And then the recursion is simply given by jk of x, some state x, is given by the minimum. We want to choose the minimum, so that whatever the adversary will choose over the w's is still the best possible. Yeah? So the adversary, we know that after we have chosen this, the adversary will choose the W. So we should choose a U so that the adversary cannot make it very bad, right? So we will get this equation. And the cost to go is also evaluated at this point x, u, and w. So we get a min-max problem. Yeah? And we would also start at the terminal cost if there's a terminal cost as before. If there's a terminal cost for our horizon. So we would just have this extra operation max of w, and that deals, so to say, with all our uncertainty. And the other case would be stochastic dp. It's very similar. And there we would get nearly the same equation. We also minimize over u, and then we will have our functions x, u, w plus j, k plus 1, f of x, u, and w, possibly with an index depending on time. But now we know that the adversary will not actually be influenced on what we chose, but it will just be stochastic. So the other player, so to say, will just do an expectation operation over the variable w. And this is the expectation value that we want then to minimize. Yeah? So this is minimization of the expected value. So for me, personally, this is the real beauty of dynamic programming is that it can be easily extended to these cases. So you could actually look at stochastic optimal control problems and also worst case optimal control problems from the dynamic programming perspective. And it's I didn't write down the original problems that we want to solve with that because it's more tedious to write them down than to write down the solution to them, so to say. But of course, this is just an equation that the optimal cost to go for these problems would need to satisfy. So this is maybe I should also say what this expectation operation means. Of course, you know it, but just to be sure, the expectation of some function which I call maybe a function phi of x, u, and w, which this function is, could be the integral over all of the space of w's, each weighted with a probability density function that I call rho, and it could still be conditional on the x and u values. So it could be a Markov chain. And then here's the phi, of course, x, u, w. So it's just a weighted sum of all possibilities. Yeah. Of course, if we have finitely many states, finitely many disturbances, finitely many controls, then all this will just become a sum, and these things can be easily computed even. Without the combinatorial explosion. And if you have a grid in state space, well, it's just the same complexity as before. There is one, I mean, if all states and controls are finite, there is the extra cost is just this averaging over the possible outcomes, or here the worst case. So it's just a multiplication of the number of W's added to the complexity, but no combinatorial explosion, nothing really bad. So for finite state spaces, this is a really beautiful thing. And it gives you the stochastic optimal control problem solution. So this is something I will not go into detail, but I wanted you to know about it because in case you encounter such problems, this would be the way to solve them. Yeah? Somehow, what I wanted to present next is still fitting, very much. But it would need about 10 minutes more. Would you digest that before the break? Better break? Good. If at least one person wants a break, then we do now the break. We have a 10-minute break. Okay? Yes. So I wanted to discuss some interesting properties of the dynamic programming recursion with you. And the perspective that we will now take is really what is at the essence of dynamic programming is that you start with a function in state space and you make from it another function in state space. That's what we have to do in each recursion step. So let us summarize this map using an operator which we will call T. So let me just start the chapter by saying the section 8.6 is about interesting properties. And these are shared by any of the presented dynamic programming variants. So the first let us first just define. So what we do is, you remember what we do is dp maps, basically what it does, maps jk to jk plus 1. Now that's what it does, and we will summarize it in the form an operator, and we call this operator tk. Yeah? And this operator acts on a function jk plus 1 and will give a function jk. So basically what we could write briefly would be just jk is equal to t acting on jk plus 1. And this t could be time depending on our system, if it's time dependent or not. So this is just a shorthand for the equation that we had before, and maybe we could define it. So tk of any function j evaluated at the point x is defined by the minimum over, and now I will just state it in the deterministic form, minimizing over all u plus j evaluated at fk of x and u. So you remember that was the dynamic programming recursion, and if you think of it from this perspective of an operator, then the input of this operator is the function j. Yeah? The data of the operator is the stage cost and the stage transition, and with these things together it will create the next function, the jk plus 1, as a function of j. Yeah? So tk maps functions or maps from the space of functions and these functions would be functions j that are given as a function from the state space, which we abstractly wrote x, and they map into R infinity, which was the extension of R with respect to infinity into itself. So in case we have a finite dimensional state space, it's just accepting a vector, because you can represent it by a finite number of numbers, right? Every state location you have one cost to go. And it takes this vector, processes it with this equation, and gives you another vector of the same dimension. Yes?
Shouldn't jk plus 1 equals tk of jk, or am I mistaken?
Sorry, here, this one?
Yes.
No. It's the other way around because of our counting. You remember we had the time index starting at the end, and we go one time step back. So in the this is we used the jk on that side and the jk plus 1 on the other side. Okay, sorry, I confused it actually with the matrix Riccati recursion, but because we start at the end, we always count down, so to say. But of course you could also, now it's just an operator and you can do whatever you want with this operator. So you could also renumber these things if you like. But the numbering we had until now was this one. And this time index, if it depends on time, would really be depending on the system dynamics, if they are time dependent or not. But what I will do, I will for simplicity drop this index, k from tk. Yeah? So I will just write now t of j. And for the case where we have stationary problems, of course, this will be already everything. And the stationary Bellman equation in this form, from this perspective, how would we write it? If we use this operator t, we would just say the stationary Bellman equation is just given by the operator equation that maps a j onto itself. Yeah, so that would be the stationary Bellman equation in a very compact form. And so now the question is if this operator has some properties that are worth mentioning. And there are two that I want to discuss with you. And the first one is something that holds always, and that is called monotonicity. And it's also very intuitive, but it's just a useful property which you can use if you want to establish things like convergence of dynamic programming recursions, or also stability of MPC schemes. So it's really a useful thing. So this is about monotonicity. And it just says, regard j and j prime. So just two value functions. Yeah? So these are functions from x to r infinity, right? So just such functions. What we will assume, or actually the theorem says if one of them is bigger than the other, if j is bigger than j prime. And of course we need to define this relation. What do we mean by one function being bigger than the other, point-wise? Yeah, so this relation we define by just saying jx is bigger or equal to j prime x for all x in the state space. Yeah, so if we have that, that means if it would be a vector, every element is bigger than the element of the other vector. If this holds, then, interestingly, also just t of j is bigger or equal than t of j prime. So it's monotonous. So if something is bigger, then after the operation t, it will still be bigger. And that is very easy to prove. Let me just do it, and I think I will extend it a bit from how it was done until now in the script. So tj of x was defined in that way. So please note I use the square brackets to denote the operator acting on a function, right? And then the round brackets to evaluate the resulting function at the value x. So this thing was defined by the relation that we had above, so I will just bring it here. Actually, maybe I will not bring it here, but I will just state it's actually L of x and u star of x. Maybe I just say u star, the optimal value, right? Plus j of f of x and u star. And u star minimizes, of course, with respect to that cost. U star being the minimizer. So, of course, you have the formula above. I put that the optimal value in, and then, of course, I have the same value. But now I observe that because my function j prime is bigger, it will also be bigger at that value, right? So I could just say this is trivially with the same u star, j prime of f of x and u star, because every single element of the j prime will be bigger, so this relation will just hold. Yeah? And now I could say, okay, this U star is not minimizing that cost that I have here, right? Because there's now the J prime. But if I exactly, so I made the sign wrong, right? Sorry. So I just said this is, the J is bigger than the J prime, so the J prime is smaller, so then this J prime will be smaller. So, sorry, so this was mixing. I had the sign wrong. So this relation is trivially true, just because for that value where I evaluated it will be true, and it will be true for all values. And so now I could also minimize this expression here with respect to the U and find even a better one, but it can only become smaller. So this is actually, if I minimize that expression over U, it can only become better. Yeah? So, and this is absolutely what would be the T applied to the J prime function, evaluated at the value x. So that is the proof of the monotonicity preservation, and roughly it's also very intuitive. I mean, if you have two optimization problems, and let's say the terminal cost, for example, in one is just bigger than the terminal cost of the other, you immediately think all the solutions must be bigger, right? Because the terminal cost is bigger and all the other costs are not changed, so can be only bigger or equal. So it's a very intuitive thing that the value function, so that a bigger value function after dynamic programming is actually resulting in a bigger value function again. But that's something I would like you to know about. So the short statement is this: if J is bigger than J prime, then Tj is bigger than T of J prime. Okay? So that's what we call monotonicity. And then there's some other property which is much less popular and not so known, actually, but which I think can be very quickly and elegantly proven and also used in some cases. And that is a bit more specific, I should also say. And it's only regarding linear systems. But it's a quite strong possibility. Actually, I could call it convexity preservation. And it's related to, for example, in linear quadratic problems, we had a convex quadratic cost to go, stage cost. And at the end, we ended up with these positive definite matrices P, which also represent a convex function. Now the question is this maybe a general feature that's intrinsic to dynamic programming? And the answer is yes. What we need to assume is actually a few more things. So assume that the system is affine in the variables x and u, for example, linear. So what we will assume is that f of x and u and maybe w, so it could depend on something, is given by a matrix A that could depend on w times x, a matrix B that could depend on w times u, plus a vector that I call c, little c, times, which could still be depending on w in an arbitrary way. Yeah, so in this case of uncertainty, I would even make it dependent on w. So I don't care about the dependence on w, but it's affine in x and u, both. Yeah? And of course, linear systems are a special case of that. And stage cost, so the stage cost L, x, u, w, is convex in x and u. So if you don't have uncertainty, for example, these quadratic stage costs, they would be convex functions if we have positive semi-definite matrices. So if these things are, I mean, the f and the L together, they define the operator T, right? So then T preserves convexity And that means that if we have a convex J, that means T of J is convex if J is convex. So that if you start with a convex cos J, then the result after one dynamic programming step is again a convex function. And for linear quadratic problems, we have implicitly used that, but of course, this is a much more general feature. Yeah? Which also holds, by the way, for convex constraint sets, because also a function can be convex if it's extended to infinity, as long as the domain where it's finite is a convex set, and the values form a function that is convex on this set, then you still have a convex stage cost. So this is all even applicable to constraints and so on, as long as they are described by convex, they are convex constraints. Okay, so how do we prove this? And what we do here is actually we will note, but maybe we should look at what we want to do. I mean, we have this function that we need to look at is L of x u w plus, and then we had here J of f u and w. So this is somehow what we need to regard, and then we can take the worst case, the maximum with respect to w, or the average with respect to w, and then we minimize with respect to u. So let's first analyze this function. So we regard that function. So this function, under the assumptions that we made, this is convex in x and u, right? This thing is linear in x and u, and then the j, if we assume that the j is also convex, then it's an affine function in x and u that we plug into a convex function. So this whole thing is convex in x and u. I should say for any fixed w, this is convex in x and u. So in the variables x and u together, it's a convex function. So now if you average it, if you take an expectation over all possible w's, it's just a weighted sum of convex functions in x and u. So the expectation will preserve convexity. Also, if you maximize over w, because the maximum of convex functions is also a convex functions, the expectation or the maximum will both be convex functions. After averaging over w or maximization, so averaging is actually for stochastic dp, or maximization, and maximization would be for robust dp. After you have done that, it is still this factor j of x u, which we get then, is still convex in both variables, right? In x and u. So convexity is preserved until now. And then after, this j tilde will be either the average or the maximum, or if we don't have uncertainty, it will just be this expression that we have here. And then t of j at x is given by the minimization over u of this function j of x and u, like before. And now this is minimization of a convex function that is convex in two variables, but we minimize with respect to one. And that, by another theorem of convex analysis, gives you a convex function as well. Then is convex is convex as well. So if you have a convex function, I think the intuition behind it is not the topic of this course. We discussed it a bit more in the numerical optimization course, But roughly speaking, what minimization, I mean, if you have a two-variable function, a convex thing, right? Minimization over one of the variables, if you think of two variables, then I have one dimension for the function. One variable in this direction is maybe the x, and the variable in that direction is the u. So if I have now this function in x and u, and I minimize it with respect to u. U is in this direction, okay? U points to u, so to say. And what you would see from that, from this three-dimensional object from the side, that would be actually the minimizer with respect to u. And of course, it's basically a projection of a convex set that you see from the side, and that therefore the minimization over u gives you a convex function as well. So that's nothing I want to prove or whatever, but it's a basic fact from convex analysis. But it leads to this remarkable thing that independent of the dependence on W, for affine systems and convex stage costs, we basically get convex cost-to-go functions all the time. And that, for example, implies if you have a linear system with a lot of inequality constraints, that your set of feasible states will remain a convex set. I mean, the states from which you think of this car, where I said if you are in front of the wall with a too high velocity, this will be a forbidden state, and if you are somehow far enough that you can still brake, then you will have a feasible point. So you could make in state space, you could mark all points that lead to, that can optimally still be controlled to a finite value, or those that lead you to invisibility. And this set is actually a convex set. And the cost on this set is a convex cost function. So it's a quite remarkable fact for linear systems and convex constraints and convex costs. Okay, so that is without much direct practical use, but that's useful to know. And the most important application we had already was the linear quadratic regulator. It's an application, so to say, implicitly, it's an application of that fact. Mm-hmm. Yes?
So would that also work for quadratic functions if J was quadratic?
Yes, exactly. And basically, you remember just before the break, I mentioned at some point we expect the P to be positive definite, right? That's exactly what I basically, here we have proven it. Yeah? So if we have a convex stage cost quadratic, a linear system like we had there, then the J, and the J was a quadratic convex function as well, then after one time step, this dynamic programming will still be giving us a convex function. So if you apply it infinitely many times, which we did for the linear quadratic regulator, it will remain a positive, at least semi-definite. We just proved convexity, right? So it will remain describing a convex function. So it will never be something like an indefinite function that has negative curvature. Mm-hmm. Yes?
That also hold, I was trying to ask that
yes.
For quadratic systems. So
quadratic
systems that are linear parameters?
No. It doesn't hold. No. There is, I mean, maybe someone has proven some properties which hold for other systems, yeah. But this convexity preservation really builds on the fact that we have here linear dynamics in states and controls. Because, I mean, what I need is that this function J, when it's convex, is convex still if I concatenate it with the J, with the F. And this is, I mean, it's only possible if I don't want to make more assumptions on this J. It's only possible if this F is affine. So if this F is, for example, something like a convex quadratic function monotonously increasing, I could probably define some things on this J, but it will not. I mean, the beauty here is that I start with any convex J and I will get a new convex J. So even if I apply it 2 times, it will remain convex. And I think, one could try to establish some properties, but they will most likely not make the J belong to the same class. It could be convex plus monotonously increasing and so on, but I don't. Okay. It's possibly interesting, but I think this is like the main practically useful thing to keep in mind. So if you have a linear system and convex costs and convex constraints, the cost to go will be a convex function. That's the main message here. Maybe one thing that I should mention, just why could it be useful? So sometimes people, I mean, what is the nice thing about convex functions? Convex functions look like this, right? And of course, they are as complicated as other functions. I mean, if you want to represent them, that you would still, in theory, need to grid them somehow. Yeah? But because they are convex, there are some other properties that they have. And one of the most fundamental ones is that you actually, if you find a supporting hyperplane, like basically a tangent, then it will be always below your function. Yeah? So you could actually approximate your function, and that's what some approaches do, with a few supporting hyperplanes. And then, of course, you get and you could think this is an approximation of your function. Of course, it's not the right function, but anyway, if I grid my function, it's also not the right one, but this might be more memory efficient if I just say I have here these 5 affine parts, and the maximum of these 5 parts is an approximation of my convex function. And then I take that representation, which just needs 5 vectors in that case, yeah, instead of maybe 100 grid points. I put that into this operation. I do some massaging of my equations, and at the end I get another piecewise representation, which might have the property that it's also a lower bound of the true one, and so on. So I can actually use that for approximating my function differently than on a grid. For example, by these linear pieces, these supporting hyperplanes. So that's one algorithm that is also sometimes used. And that leads to a technique that's called we call polyhedral DP. Yeah, so that's basically convex polyhedral representations of your cost to go, and they remain polyhedral for some assumptions. Yeah, I think I will not go into much detail here, but instead I wanted to still share with you another exciting relation, which is the thing I definitely need to present to you. So this cost to go, I think, hopefully you have, like I do now, like this image of I visualize it like a convex, but it need not be a convex function, but basically it's a function, the cost to go from here to the end. So now the question is, if I have the initial value fixed, and I know all my cost to go functions, I can of course compute my optimal trajectory, and then I can look at this optimal trajectory, and I could ask my question: what do the values of the cost to go function along the optimal trajectory, what would they need to satisfy? And there is an interesting relation that actually gives us another meaning for the Lagrange multipliers. And this relation is actually that the gradients of the cost to go along the optimal trajectory, they need to be related with each other. And they are actually related as the multipliers in the other optimal control problem, so that we can identify actually the gradient for the value function at an optimal trajectory with the multipliers in the direct approaches that we had before. So I want to discuss the gradient of the value function. Sorry, I say value function, and I didn't really specify. I called the value function, sometimes I said the cost to go, right? I don't have the word here, but I always call this J the cost to go. So, often it's also called the value function. Yeah? So it's just another name for the same object. So what I want to regard is an optimization problem with a fixed initial value. Yeah. So I don't state it again. But if you remember what was dynamic programming, what it did, it was just saying that along the optimal trajectory, or no, not even along for any state, we would have this relation. The last value function is just given by the terminal cost. And then we would have these jk at x being given by minimizing over L of x u plus jk plus 1 at f of x and u. I think I can afford to add the index. No, I don't have the index here, so let's drop it just for simplicity. So this is the relation that defines basically all the value functions. And now I could look what happens at the optimal trajectory, right? So at the optimal trajectory, I have x0 is given by the initial value, and then the control, the trajectory xk plus 1 is given by xk and uk. But the uk is, of course, the optimal one. So I know that the uk is the argument, and let's assume it's unique, so I can just say argument that minimizes the function L x k over all u plus j of f of xk and u. And here's jk plus 1. Yeah, so this uk, the specific value that it takes, should be the minimum of that function. And so now I assume differentiability of that function, and then I actually, locally at least, because it's a minimum and it should be unique, that will imply the first order necessary condition of optimality. So that means that the gradient of that function L at the optimizer, which is uk, plus the gradient of that thing. What is the gradient of that thing? Maybe it's actually, gradient is transposed Jacobian, so I put this Jacobian to the front, and so what I have here is df dx at xk uk transpose times the gradient of jk plus 1 at the value, and now at which value? At the value at which I'm here, which is f of xk and uk, but that is also xk plus 1, right? So I could directly say xk plus 1 here. So this relation, that should be 0 because of optimality. So now basically I assume differentiable f, L, and E. So all my things are now differentiable functions. So I have already one relation, but that's not the end of what I want to derive. I mean, I have a relation that I know that at the optimal trajectory, this relation should hold. I mean, my gradient of the value function here, multiplied with this Jacobian here, should equal somehow the negative gradient of the stage cost with respect to u. Also interesting already. Sorry, this was with respect to u. Sorry. Here's a u derivative. And now I could look at what do I have along the trajectory. I mean, I can, of course, just say along the trajectory, I could just plug in the values here. So what I will have is that Jn of the value xn at the tree will just have the value xn, right? So that's clear. Then also for the jk at xk, I know that at the optimal trajectory, the minimizer of that whole thing, that will be the uk, so I will actually have this relation. Xk uk plus jk plus 1 f of xk. No, sorry, here I can directly put the xk plus 1 if I want. So I make it a bit shorter, right? So this relation I have. For example, one consequence of that already is that if the L is empty, so if there's no stage cost, and I only have a terminal cost, then along the trajectory, the values of the value function will always be the same. So if I have only a terminal cost in a problem, then if you think of this trajectory as a function that moves, so to say, in this the image that I have is the following. So the state space is a one-dimensional thing. The value function is something in this one-dimensional space. And now I have the time steps. And so what the value functions together form is a valley, so to say, right? And along this valley, if there's no stage cost, I know that I will move on one fixed altitude, so to say. So that would be one consequence of that relation. But what is actually more exciting is if I differentiate these relations with respect to the state, I get another relation, and that is the core which I wanted to derive. So of course I can differentiate that thing with respect to xn, and I will get that the gradient at xn, so these gradients should be equal. That's actually, sorry. So that's a relation that we get directly from this definition, right? What is a bit more difficult is this relation here, because it's involving the minimization. Yeah? So, and the u itself depends on the value x. So what happens if I differentiate that whole thing with respect to u? I will actually need to differentiate, so nabla j k at xk. Now, with respect to its only variable, it's always derivatives with respect to k. So what will it be? And maybe it's nicer to actually work with the transpose, because then it's really like Jacobians and I can really use the chain rule. So what I need there is, maybe I directly use the abbreviation that we had before with this j tilde, right? So why don't we call the function j k tilde of x and u as being the function which is L of x and u plus j k plus 1 of f and x and u. Yeah? So that's like the same definition we had before. So I give this definition, and then I note that this statement that I had here at the bottom, so this actually means that I have the gradient, so dj tilde by du at the trajectory, on the trajectory values should be 0. That's basically what this means in shorthand. Yeah? So just to write it a bit briefer. And here I would now have the minimization. So what I can actually, I could write this equation as, maybe I first write, so I will not do it, but I will also define, so I will just say j k of x is equal to j tilde k of x and of u star of x and uk star. So it's basically the minimizer which depends on x as well. So that's the minimizer of this problem. And now I could ask the question, what is the gradient of this whole thing at the optimal solution? And so what I can do is I can differentiate that whole thing inner and outer. So what I get is dj tilde by d, so with a k by x, plus dj tilde k by du times du star by dx, right? This is just a default computation, but now because I'm only interested at the value xk, I can actually just evaluate that. So maybe so that's a partial derivative of that whole function. So this is actually the gradient of L at xk and uk. uk is the optimal value, so I can plug it in here. Plus the gradient, and now I have the same thing before, df by dx at xk and uk. This whole thing, so there's no index here, but transposed, times the gradient of this j, nabla j. This is stupid what I do here, because now I mix my notations, right? So I had transposed this already, so I need to just put here the gradient of j k plus 1, transpose, and at xk plus 1. I transpose it, and now I multiply it with df by dx at xk and uk. So now I have this term. And now I note that at the solution, because of this relation, this thing will be equal to 0. So it's plus nothing. So it's plus 0, independent of how the u depends on x. So what I get as a relation is a relation between the gradient at the point xk and the gradient at the point xk plus 1. And this holds for all k from 0 to n minus 1, this relation. So this is something that should hold at the optimal trajectory. And the beauty of that is that if I collect all this as conditions, and I maybe give another name, I just make a shorthand at the moment. I just call it lambda k. I define it to be the gradient of j at k on the trajectory, on the optimal solution. I just give it this name. And then I collect all these conditions that should be satisfied. And then my conditions are actually that lambda n should be, the last one, should be equal to the gradient of the cost at the last point. And now I have this other relation that I just derived, this thing here. I transpose it, and it just says lambda k should be equal to the gradient of L at xk and uk plus, and now I transpose it, so I have df by dx at xk uk transpose times, and now I call this lambda k plus 1. And this holds for k from 0 to n minus 1. And so I know these conditions should be satisfied for the gradients of the value function along the trajectory. So these are the gradients of the value function on the trajectory. So it's just the slope that I have while going along this trajectory. And these values, I just call them lambda now. Of course, it's a very intuitive name because you have seen these equations before. And these equations actually are the equations that our multipliers satisfy in the optimality conditions for the simultaneous approach. So if you collect these conditions, they determine uniquely all the lambda n's, right? The lambdas. And if you combine it with a forward recursion, with this one, and with this condition here, then you get actually a root finding system which was exactly equivalent to the necessary optimality conditions in the optimization context. And that's what I called in the script a discrete maximum principle. It's basically a boundary, a discrete maximum principle. So it's collecting all these equations in one set of equations, and it's something that we will see in the context of continuous time optimal control again. And there it has this name, maximum principle, or minimum, sorry, whatever you like. So it's a stupid name. But we can collect all these things, bring them into a boundary or into a root finding problem, and then we see that actually the gradients of the value function, they satisfy exactly the same relation that in the previous formulations the lambdas satisfy, so we can actually identify them. And the lambdas that we get in the other approaches are identical to the gradient of the value function. Maybe I should say that this is also not so surprising from the other perspective that you could take. And the other perspective is, what was a lambda? A lambda was the sensitivity of the optimal solution with respect to a perturbation in the constraint. So if I move a bit my state, I mean, if my state equation would be perturbed by an epsilon, then I would move up or down my value function. And so this gradient was actually exactly what the lambda expresses. So the lambda expresses how much does your objective change as a function of modification of the constraint. So also from that perspective, you would get to the same result. Yeah? So the bottom line is the value function has a very strong relation with the multipliers, and the multipliers, so the gradient of the value function along the trajectory are basically the multipliers from the other approach. Okay, so we are at the end, and I want to make an outlook. Next time I wanted to still present you an approach that's called differential dynamic programming, which builds on these ideas, but basically is just another way to solve the discrete optimal control problem with the Newton type method. But it has the name dynamic programming in it, and so I want to present it in this chapter. And people sometimes know about it, even though they don't know about Newton type methods, because in a different community people talk a lot about differential dynamic programming, and I want to make you aware of that approach so that you can understand what is meant by it. And afterwards we go into continuous time. So I should say that the next week I go to a workshop on numerical optimal control, and for this reason I skip the lectures. So you have a week of free time. You could use it to rehearse the script and learn a bit and maybe work on, I don't know. The exercise probably needs to be, how do we do it? There is an exercise next week. So the exercise is on dynamic programming. So this is something you could do next week, and otherwise just relax and recover. And maybe those that do projects, they could start to think about suitable projects that they would like to work on. Something which is related to an application problem that you find exciting. Maybe also solving it with one of the algorithms that you find exciting. So something that you really like to work on, and that should take not an excessive amount of time, but that would be exciting enough for you to make maybe a few evening hours just working on that problem. So maybe you can start thinking about projects. I wish you a nice week, actually. Thank you.